Hello everyone and welcome back to Educator.com. I'm Dan Fullerton and in this lesson we're going to talk about current and resistance. Our objectives include understanding the definition of electric current, relating magnitude and direction of the current to the rate of flow of electric charge, relating current flow, drift velocity, and the density of charge carriers in a conductor, relating current and voltage for a resistor, writing the relationship between electric field strength and current density in a conductor, describing how the resistance of a resistor depends upon its length and cross-sectional area, as well as the material it's made out of, and finding the resistance of a resistor of uniform cross-section from its dimensions and the resistivity of that material. So let's dive right in. Electric current is the flow rate of electric charge. Units are in coulombs per second, which we also know as amperes, which are given the symbol capital A, and oftentimes you'll hear that referred to as amps. Positive current flow is the direction of the flow of positive charges, which can be a little bit confusing, realizing that in most of the circuits you're going to talk about, it's actually electrons which are moving. So the direction of the charge carrier flow in most circuits, electrons, is opposite what we call the direction of positive current flow. Formally, current, capital I, is the amount of charge passing through a point at a given time, or dq dt, the time rate of change of charge. So, let's talk a little bit about drift velocity. In a conductor, electrons are in constant thermal motion. Net electron flow, however, is zero because that motion is in all directions. It's random, so they all cancel out. But when an electric field is applied, a small net flow in a direction opposite the electric field is observed. The average velocity of these electrons due to the electric field is known as the electron drift velocity, Vd. And this is typically much smaller than the speed of that constant random thermal motion. To give you an idea, let's take a look at the derivation of current flow. We'll consider a uniform conductor of cross-sectional area A and apply some electric field E. And let's draw that in here, an electric field. Now, we'll define capital N as the volume density of charge carriers in this material. So, electrons in the conductor move randomly with thermal velocities. We talked about that on the last slide, roughly 1,000,000 meters per second. They're moving pretty quick, but it's in all random directions. When we apply this electric field, however, there's some small net movement of electrons opposite the direction of the electric field. And that speed might be on the order of, say, 0.5 centimeter per second compared to that thermal motion of 1,000,000 meters per second. Well, if we define N as that volume density of charge carriers, that means the electrons contained in some volume. Let's highlight it here in yellow, but let's say that that is their drift velocity, Vd, times some time interval, delta t, times that cross-sectional area A. The electrons in that volume are going to pass surface A in time t. From that, the total charge that's passing A is equal to the product of the volume passing surface A, the carrier density, and the charge on each carrier, which we're going to call little e. So we've got this amount that we have to deal with, Vd t A. And if we want the charge that passes A in that period of time, that's going to be that carrier density times the charge, E, that goes with each of those charge carriers, typically an elementary charge, times that volume, Vd TA. And since current is charge per unit time, we can say that current flow then is going to be N times our elementary charge, times that drift velocity, times that cross-sectional area. Or I oftentimes write this E as a Q as well. So you may see it in this form, NQ VDA, the current flow derivation. We could also look at this from the perspective of current density. Current density through a surface is the current per area, and it's a vector quantity, usually given the symbol capital J. So capital J, the current density, would be that carrier density times the amount of charge per carrier times the drift velocity Vd which implies then as well that current flow I is going to be the integral over that cross-sectional surface of J dot dA. So you can relate current flow to current density. Now, as we talk about this, we're also going to bring resistors into play. Resistance is the ratio of the potential drop across an object to the current flowing through the object. Objects which have a fixed resistance that's not a function of the current or potential drop are known as ohmic materials, and they're said to follow Ohm's law, an empirical law. Now, R equals V over I. Therefore, Ohm's law, V equals IR. Just a rearrangement of that. The potential drop across a resistor is equal to the current flowing through it times its resistance. And if this is a constant slope, a constant resistance regardless of the current or potential drop, we say that the material is ohmic. If we didn't have a straight line, we would call that material a non-ohmic material. So what happens when you have a wire? The resistance of a wire depends on the geometry of the wire as well as a material property of the material the wire is made out of, known as its resistivity, given the symbol rho. The units of rho are ohms, omega sign, times meters. Now, resistivity relates to the ability of a material to resist the flow of electrons. So if we have a resistor of some length L and cross-sectional area A, we can find its resistance, capital R, is the resistivity times its length divided by that cross-sectional area. You can almost think of it, it's kind of like water in a pipe. If you have a thicker diameter pipe, you have less resistance to water flow. Thicker diameter wire, less resistance. A is in the denominator. The longer it is, the harder it is to push things out, the higher the resistance. Same thing with the water pipe. The longer the pipe, the more resistance to water flow. So very, very similar and a nice analogy for helping to understand these qualitatively. Let's see if we can't refine Ohm's law just a little bit. If we start with V equals IR, but we also just said that R equals rho L over A for a cylindrical resistor, then we have V equals I rho L divided by A. But we also know, because we have a uniform material, that the electric field is going to be the potential drop divided by the length, that our electric field then is going to be rho times I over A. But this I over A, current per area, well, that's the current density. So this implies then, because current density equals current flow divided by area, we could write then that our electric field is equal to our resistivity times our current density vector. Going further, we can even talk about the conversion of electrical energy to thermal energy. The work done, or energy used, is charge times potential difference, which implies that the time rate of change of that, the rate of change of the work done with respect to time, is going to be the derivative with respect to time of QV. But we also know that power is the time rate of change of work done, dW dt. So we could write then that power is equal to, well, potential should be a constant, V dq dt. But dq dt, we said, was current flow. Therefore, we can write that power is current times voltage. Or, using Ohm's law, V equals IR, replacing V with IR, power equals I squared R. Or, using Ohm's law rearranged again, if I equals V over R, let's replace I squared with V squared over R squared, we determine that power is also V squared over R. So we have a couple different derivations for the rate of change at which that energy is expended, which we call power. Let's take a look at an example having to do with the silver wire. A silver wire with a 0.5 millimeter radius cross-section is connected to the terminals of a 1-volt battery. If the wire is 0.1 meter long, determine the resistance of the wire. It gives us some information: the resistivity of silver, its molar mass, and its mass density. Well, resistance is rho L over A, where our resistivity here is 1.59 times 10 to the minus 8 ohm meters. Our length is 0.1 meters, and our cross-sectional area is going to be pi times our radius squared, which is 0.0005 meters squared, for a resistance of 0.00202 ohms. Well, let's see if we can't extend this example a little bit further. A silver wire with a 0.5 millimeter radius cross-section connected to the same battery, same length of wire. Determine the current flowing through the wire. Well, current is potential divided by resistance. We have a 1-volt potential, and we just found our resistance, 0.00202 ohms, gives us a current flow of around 494 amps. Let's take this even further in a slightly more detailed calculation. Same wire, but now we're asked to find the drift velocity of the free electrons in the wire, assuming 1 free electron per atom. Well, in order to find the drift velocity, we first need to know the charge carrier density, and we'll determine this by dividing Avogadro's number by the volume of a mole of silver. Then we can find the drift velocity from our formula for current. So let's start there with our charge carrier density is Avogadro's number divided by our volume, which implies then, since we know the resistivity of silver, or our molar density of silver, is going to be our molar mass divided by volume. Our volume then is going to be our molar mass divided by rho. Therefore, N is going to be equal to Avogadro's number, rho silver, over its molar mass. All right, so then we can look at the current flow. I, we know, is N times the charge per carrier, V, drift velocity, A, and we want drift velocity, so VD, drift velocity, will be I divided by NEA. But we just found N up here, so we'll plug that in to determine that VD equals I M over NA rho silver EA. Or solving numerically, that's going to be, we've got our 494 amps for our current. We have our molar mass, 0.1079 kilograms per mole, making sure to put this into our standard units. Oh, by the way, 10.5 grams per cubic centimeter, that's going to be 10,500 kilograms per meter cubed when we get there. So we've got to divide all this by Avogadro's number, 6.02 times 10 to the 23rd, times our mass density for silver, which we said 10,500 kilograms per meter cubed, times our charge per carrier, that's our elementary charge, 1.6 times 10 to the minus 19 coulombs, times our area, which is pi r squared, so pi times 0.0005 squared. Put that all very carefully into your calculator. I come up with a drift velocity of about 0.067 meters per second. A little bit more to do on that one. All right, let's go one step further here with the silver wire. Determine the average time required for electrons to pass from the negative terminal of the battery to the positive terminal. Well, we found the drift velocity, and velocity is distance divided by time. So then time is going to be distance divided by drift velocity. And if we have to cross 0.1 meter, and our velocity is 0.067 meters per second, that means it's going to take right about 1.49 seconds for those electrons to travel that distance. All right, let's take a look at one last example problem. A 12-gauge aluminum wire with a cross-sectional area of 3.31 times 10 to the minus 6 square meters carries a 4-amp current. The density of aluminum is 2.7 grams per cubic centimeter. Find the drift velocity of the electrons in the wire, assuming each aluminum atom supplies one conduction electron. So starting off with what we know, our area is 3.31 times 10 to the minus 6 square meters. Our current is 4 amps. Our rho is going to be 2.7 grams per cubic centimeter, our density, or if we convert that into kilograms per cubic meter, again, that's going to be 2,700 kilograms per meter cubed, standard units. And our molar mass is 27 grams per mole for aluminum, which is 0.027 kilograms per mole. So we can go back to what we did in example 3 to get us at least partway there in this problem. We know that current is NEVDA, and we went through and we also found then that drift velocity is current times that molar mass over Avogadro's number times our density of aluminum times our charge per charge carrier times A. And if I substitute in my values, we end up with, well, our current was 4 amps, our molar mass was 0.027 kilograms per mole, Avogadro's number 6.02 times 10 to the 23rd. We had our density 2,700 kilograms per cubic meter. Our charge per carrier, 1.6 times 10 to the minus 19 coulombs, our elementary charge. And our cross-sectional area, it gives it to us here, 3.31 times 10 to the minus 6 square meters. And I come up with a drift velocity of right around 1.25 times 10 to the minus 4 meters per second. All right, hopefully that gets you a good start with current and resistance. Thank you so much for watching Educator.com. We'll see you very soon. Make it a great day, everyone.